So hey nerds, this is Suman, and in this video I am going to show you, might be, I am not sure in this particular case, but might be how a mind of physicist actually works. So I am not a physicist, so I do not have any degree for that, right? And if you compare me based on the degree, I might not be the one. So if you don't compare me with the degree, I might be one of them. So basically, in this video, I'm going to show you an equation how a physicist might think in a three different versions of the same equation. So I'm not doing here the very much complicated mathematics or something else. I'm just doing the simple concept. If you are a student of class 12 science, you had known the relation of decay equation. So this could be very much easy for you in order to grasp the knowledge, right? So basically we are just doing the expression of radioactivity, and I'm going to show you how a mind of physicist actually works. So how they can see something that the ordinary mind doesn't see. So you can actually think I might be a physicist, right? So in order to do that, we just need an equation, and we have to solve the equation, and we get the final result, and we have to look the same equation in very much different perspective here. It is going to be very much beautiful and elegant result. So how a physicist can see a structure, the looking how it can see a structure in very much different ways as compared to the normal equation. So if anything, it can be represented in terms of number, can be represented in terms of mass, and mass and energy are the same thing. So you can replace the mass terms with the energy term. So there is a triangle there would be a triangle that connecting all these points, that if you have a number and you have energy, sorry, you have mass and you have energy. So isn't that very much interesting? So I would like to show you some elegant result of radioactivity, and it might be the one of the process that how a mind of physicist actually works here. So let us dive into the video. So nerds, let us dive into the very much detailed structure of law of radioactivity. So I'm just starting from the law of radioactivity, right? So I'm just starting from law of radioactivity. So basically it tells us that the rate of disintegration of atoms, so the change in atoms with change in time, is proportional to the number of atoms at that time. So this is what the law of radioactivity tells us, right? So I would like to confirm one thing, that let us assume we have a sample of radioactive substance here, some radioactive sample, right? And the sample at t is equal to 0. So it is because initially, let us assume initially there is n not number of atoms present. So it is in the radioactive substance, and the measurement starts from t is equal to 0. And after some times, the radioactive substance decays, and the number of atoms going to change. So at any time t, let n be the number of our atoms present in the sample. So basically what the law tells us, the rate of disintegration of atom, the rate of disintegrate, the meaning how much it is going to cut off, or simply the rate of disintegration with respect to time, is proportional to the number of atoms at that time. So I can write my rate law is dN upon dt is directly proportional to the number of atoms at any time t, right? So basically I have to use here negative sign. Why? Because if I had 1000 atoms, and let us after some time it would be 900, so you have to find the change, and in change is going to be 900 minus 1000, and it is going to be minus 100 atoms, and you haven't seen that minus 100 atoms. So in order to make this sign positive, we have to use here is positive. So dN would be our negative, just to ensure that the fact that we have to use sign negative just to make it, and this negative and negative will make this quantity over here is positive, right? Up to here I guess you have understand something. So now in order to remove the proportionality sign, we have to add some constant. That would be our lambda n. So lambda is going to be our decay constant. Decay constant. Right? So it would be our decay constant. Okay. Now I would like to take this negative sign here. Negative dn upon dt is minus lambda n. Right? Okay. So I am going to do something very much non-intuitive thing that a mathematician would never do here. I am multiplying this side by dt and again multiplying this side by dt and I am cancelling this. A mathematician will never do that. A mathematician will never do that. So what I am left here is dn equals negative lambda n dt. Right? Okay. So now I would like to take this n over here and I got dn over n equals negative lambda n dt. So this might be my generalized equation of this, or let's say from generalized equation of this. So what do we have to do now? We have separated the variables. So the variable here is n and the variable here n is t. So so in order to get the solution of this differential equation, we have to integrate it. So I have to integrate. So the integration depends on your choice whether you do definite integral or indefinite integral. If you go through the indefinite integral, you have to take the constant and constant. Suppose if we have x and dx, we get x square by 2 plus c. So this would be our definite integral. And if there is some limit within it, you do not have to add c because, and it is going to be x square by 2 and the limit is going from 0 to 1 and you do not need c here. So I am going to use within limits. So now what I am doing here, so you can actually think that what is changing here? The time is changing in RHS and what is changing in LHS? The number of atoms is changing in LHS. So the time starts from when? T is equal to 0. So the lower limit of time is going to be 0. Okay. So when time is 0, the corresponding number of atoms here would be n naught. So the corresponding number of atoms is n naught. And after some time t, the number of atoms here is corresponding here is n. So this would be my integral. So if you know the fact that integral dx over x can be written as ln x plus c. So now we have just a definite integral. So we have limits. So we do not need any constant c. So I can write it as ln n and the limit goes from n naught to n equals negative lambda t. It goes from 0 to t and we do not need any constant here, right? So now I can do something very much interesting here. So if you have integration of x from a to b, integration of dx from a to b, you can actually write it as x from a to b, and in order to substitute the value, you have to first substitute upper limit and then lower limit. So you have to write first b minus a is upper limit minus lower limit. So what we have going to here, this would be ln n minus ln n naught, right? And this is going to be lambda t minus of 0, right? I am using another identity here. I am just using an identity, bunch of identities, that is log a minus log b can be written as ln a over b. So this is of the form that is log a minus log b, and it can be written as log a by b. So this is the another identity that I am using here. So what I can write here, I can write n ln n upon n naught, and this is minus lambda t, right? So I am using another identity that if you have y equals ln x, so if you want to replace, if you want to write in terms of x, you can write x is e raised to the power y. The thing that is in LHS would be goes on it the power of e. So this is going to be my another identity. So this is of the form, and when the log goes here, it will convert into exponential, and the remaining term would be going in its power. So the final expression is n upon n naught equals e raised to negative lambda t. So the final expression is n as function of time equals n naught exponential negative lambda t. So this is my final equation of law of radioactivity. Okay, up to here, I guess nothing is very much bad. So you know this is not the multiplication, this is just the function. So n depends on time, because for different time there will be different number of atoms. So let us assume after some time 5 minutes the number of atoms is 100. After 10 minutes the number of atoms would be 50. It doesn't have to depend on this similar manner, whether there will be 49, there will be 58, there will be 20, there will be 10. So it just gives us the relation that the number of atoms left at any time t decays exponentially. So this would be the final relation of law of radioactivity. So sorry. So now I am just writing this equation here. So this is the one relation that is obtained, that is n equals n naught exponential negative lambda t, right? So this might be the relation that is found by first physicist, and there will be some another physicist who don't like this equation and he want to change it in terms of mass. So what is actually decaying here? The atoms has mass. So mass is actually decaying in each step. So how we can replace in terms of mass? So I am just multiplying both sides by mass of atom. So let us say Ma as mass of atom into n equals n naught into Ma exponential negative lambda t. Okay, and I would like to confirm you that one thing. If you have 100 electrons, or let's say 1000 electrons, and mass of electron is 9.1 into 10 raised to the power negative 31 kg. So if you multiply this number with the mass of one atom, or the simply mass of one electron, you will get the total mass of electron. You will get total mass. Total mass is going to be product of these two, n into Me. So in this LHS we get total mass left. In this LHS we get the total mass left. So this will be total mass left at any time t equals, so n naught into Ma. So n naught is initial number of atoms and it is multiplied with the mass of all atom, single atom. So we get it is m naught, the initial mass. M naught, initial total mass. Isn't this interesting? And we got exponential negative lambda t. So this would be this relation in terms of mass. So this is obtained by second physicist, right? I hope up to here it might be clear to you. So each element has a particular mass, and if you multiply it with the number of atoms, you get the total mass. So this is the total mass at any time t. So it can be written as there will be some mass m. So there must be some mass when t is equal to 0. There will be some mass m naught. So in terms of mass. So and there might be another physicist who don't like this equation. So he knows that the mass and energy are the same thing. So now he want to convert it in terms of energy. So when this thing is actually decreasing with respect to time, decaying with respect to time, what is actually changing here? It would be, the first physicist would say, no, there will be the number of atoms that is changing. The second physicist say, no, there will be the mass that is changing with respect to time. So the third physicist might think that the energy is going to decay with respect to time. So in order to get energy term, we can multiply m c squared, m naught c squared e raised to negative lambda t, right? And this is the not the relativistic mass, this is the rest mass energy. So the energy, so this is going to be the energy at any time t is E naught. So m naught, there will be corresponding energy E naught, and for m there will be corresponding energy E. So E at any time t is E naught exponential negative lambda t. Now the third physicist, this would be third physicist. This is the third physicist. So the same equation can be represented in three different versions. This is the first, this is the second, and this is the final. So a physicist actually see out of the box. He just don't memorize the formulas. He just see the pattern. The pattern goes on like this to this. So it can be written in terms of number of atoms. No, I don't like that. It can be written as in terms of mass. I also don't like that. It can be written in terms of energy. So if you have anything below this, you can actually do it below here. So this is the decay of energy or mass or number of atoms. These whole three things represent the same phenomena because all the thing decays exponentially. Isn't that very much beautiful? Everything decays exponentially. So if you want to plot the graph, for number of atoms or energy or mass with respect to time t, you will end up getting the same curve. Because even the three of them decays exponentially with respect to time. This is the beauty of physics, and this is how a physicist see a equation. If someone is doing experiment in terms of energy, number of atoms, he use this formula. In terms of mass, this formula, and in terms of energy, it is going to be this formula. So isn't this very much beautiful to you? Or might be you may not be from the background of physics and you don't like this equation, but I am the one belonging to that background, so I really love this equation. So I can manipulate the whole bunch of equation into three different versions, and I can do the experiment depending on my choice. How am I going to do the experiment? So this is very much beautiful. So this is the video that how a physicist might think. So if you like this video, make sure to like, and up to there, bye bye.